Can you guys hear me? Okay, hey everyone, welcome to another lecture of Generative Adversarial Networks. I'm Harini and Jill and I will be taking this lecture today. So what we'll essentially be covering today is a little bit more in depth as to why training GANs is so hard, what its limitations are, and how we can formulate this in a better way so that we can overcome some of these limitations. We'll also be going through different formulations of GANs and some of their applications as well. So to have a quick recap, this was how we set our problem, right? We had a large collection of images. In this case, it was human faces. And the idea was, can I generate a new image that looks real? So we basically had to understand and really identify what the underlying distribution of the data was so that we can generate new face images that looked just as similar. So in order to do this, we looked at two different types of models. We looked at discriminative models and generative models. And as we know, discriminative models essentially learn the decision boundary between classes. So it's going to try and model the posterior probability of P of y given your data. But in case of generative models, it's going to take a more holistic approach where it's going to try and model the joint distribution. And if we remember from simple math, we can write this in this way. So considering that it takes a more holistic approach of modeling the joint distribution, it also has access to this. And that is why a generative model can do both generative and discriminative tasks, because it completely tries to model the entire distribution. But in case of your discriminative models, it can only do a classification task because it only learns P of y given x. So we saw that one way we can potentially solve our problem is by using a variational autoencoder. And if you guys remember the VAE lecture, we know that the decoder actually acts like a generator, where if you sample any Z from some random distribution, typically a Gaussian, you have a generator that's going to generate data that is going to look very similar to the distribution of your training data, because that's how the decoder is or the VAE is generally trained, right? It's going to maximize the likelihood of the data, which means whatever image is being generated, it's very likely that it's going to be similar to the distribution that it was trained on. But we did notice, both in the last class and you'll see today, that there was a huge shortcoming of this. While you know that it's an image that is being generated, which has a similar distribution as your training data, there is really no way to identify whether it is a human face or not. So let's talk about what's the easiest way to check if the output that's generated by a VAE is that of a human face or not. Let's say I give you like a VAE's output now and tell you within 10 seconds you have to tell me whether it's a human face or not. How would you go about that? What's the easiest way you could do it? Exactly. You pretty much just look at it and say, hey, okay, this looks like an image of a human and this does not, right? But what we essentially want to do is exactly that. We want a model to sit in that place and we want it to do just that. We want it to be differentiable so that you can backprop your loss and then ultimately your entire system can be trained end to end. So that's essentially how we introduced GANs. We had generative adversarial networks where you have a generator that's going to generate data that's similar to your training data. And you have an adversary that's going to battle with the generator to try and ensure that it's able to discriminate between what's real and what's fake. So hopefully up until here, nothing was very surprising or out of the blue. And we're going to now look at how we formulated GANs visually. So we saw that you can again take any Z that's sampled from some seed distribution, typically a Gaussian. We pass it through a generator that's going to generate data that's very close to your training data. And the main task of the discriminator is to basically take that and say, hey, is this real or fake? And what we did next was we added a little bit of math into it. So let's look at this real quick. So the main objective of the discriminator was to say, if I get a real image, my output's supposed to be 1. And if I get a fake image, d of x is supposed to be 0. So that 1 minus d of x will essentially be 1. And we said that we'll formulate this by taking the log of the output of these probabilities. And that's what we said. So if the image is real, then the discriminator will compute log dx. And if it is fake data, then it will compute log of 1 minus dx cap, where x cap is g of z, which is what's shown in the image. And if you guys remember, that's how we ultimately came to this min-max optimization. So this is how your entire GAN is formulated. Your discriminator will basically try to maximize its output so that it has to get whatever it's seeing, it has to get it right. So if it's real, it will ensure that it's saying d of x is 1. And if it's fake, it's going to ensure that 1 minus d of x is equal to 1. But the main objective of your generator is to fool the discriminator. So it will want the discriminator to say that if I send you a fake image, you have to output a 1, which is why it's going to minimize the second objective, as we saw in the last class. So that's what these two are trying to do. They try to go against each other. And the way that we saw this worked was whenever you have two probability distributions, let's say, if this was that of your real image and this was generated, so let's call it x. We said that the discriminator will first be trained and it will find some boundary like this. And then what the generator is going to do is it's going to try and generate more images that are characteristic of this distribution, because ultimately that's what you want your generator to do. So the generator will slowly start moving this way, but the discriminator is also being trained. And so your decision boundary keeps moving, and finally you have both of your distributions would essentially overlap, and the discriminator will ultimately be still be random. So then we looked at, well, how can I find the optimal discriminator and optimal generator? And we wanted to do this because while training, you ultimately want to find what is the optimal solution to your problem. And so we said when you have two different distributions like that, the discriminator would essentially find a decision boundary, and it would be px divided by px plus pg. And this is the optimal discriminator. And we put this in our min-max optimization formula, and we essentially got this, where the main characteristic of the generator or the optimal generator is that it's going to try and minimize your Jensen-Shannon divergence. With a little bit of constants here and there, but essentially what the generator tries to do is, like we saw there, it's going to try and make the two distributions as similar as possible. So again, a quick recap on the difference between VAE and GANs. Of course, we saw that VAEs have no capability of identifying exactly whether it's a human face or not, but GANs can. But apart from that, a very important difference is that VAEs make use of KL divergence, and that's what it minimizes. But GANs make use of the JS divergence, and that's what they minimize. So it's obviously a more difficult optimization problem compared to VAE, which is simpler and faster in training. But the sort of trade-off that you do in this case is how good do you want your results to be. It's perfectly fine if you want blurry results, but really quick ones, and simpler optimization problems, in which case you can go for VAEs, but GANs are known to beat them and be far better because the results are much sharper. Okay, so these are some notations that you should be comfortable with by now, but I'm just putting this out there. I'll give you like 5 seconds, but essentially you have what the distribution is going to look like, what the generator and discriminator models are going to be denoted as, and what the outputs are going to be denoted as. None of this should be very different from what we saw in the last class, and we'll be following this moving forward. So we also saw this, the best way to train a GAN. How do you train it? You start with the discriminator, starting with whatever generator you have. Usually it will be initialized with random weights, or however you decide to initialize it. And then keeping that constant, you go and train the generator. And the main purpose of the generator is to beat the discriminators, to try and fool it. And this is what we'll be optimizing. And once we finish the entire training process and we've attained convergence, you can do away with the discriminator because you only need to generate images after that. So in code, this is how it will look. It again talks about the steps are exactly the same as what we saw in the previous diagram. The only additional thing is you see this parameter called K, which is essentially a hyperparameter. This is from the 2014 paper that introduced GANs by Ian Goodfellow. And they used K as 1, so you can essentially put that for loop away. But during your training, if you feel like you want the discriminator to be trained for a particular number of steps before you go and train your generator, then you can experiment with how many steps you really want to train it for. So another very interesting thing that was mentioned in the paper was we know what the generator tries to do is it tries to minimize log of 1 minus d of g of z, right? But what they saw was this term actually saturates very early, so the model does not really learn. And because of that, what they did was they removed the 1 minus and then they added a negative sign here. So instead of minimizing log of 1 minus d of g of z, they maximize log of d of g of z, and they noticed that this gave them more informed and better gradients in this case. These are good to know things that you can also potentially do when you go ahead and implement GANs.
Can you fix the mic? We also need to.
I think it's at the max. Is this any better?
No response.
Okay. So what the new optimization problem becomes is you have a similar structure as what we saw before, except your second term now becomes log dg of z with a negative sign here. And remember these very clearly because this is something that we'll be using going forward when we look at what the issues with training are and different types of GAN formulations. And we also looked at explicit and implicit models, if you guys remember that in the last class. So since this is an implicit model, you can rewrite d of g of z as d of x. Okay, so again, two theorems that came from training GANs is the first one, you achieve global minima of the loss if and only if px is equal to pg. And the way that you can derive this is you differentiate that huge equation, set it to 0, and you can essentially find out at what point this happens. And then when you substitute it back, you'll see that the loss value you get is minus log 4. But what's more, I guess, nice to know is if you have a good enough generator and a good enough discriminator, theoretically, you can have your distribution of the fake data actually converge or actually become similar to the distribution of your real data, which is good to know because you have theoretical backing that if you go ahead and start training GANs, you can converge and your, potentially you will get a good solution. So you're not going to be left in the dark. So another thing that we saw was why do we even need to use the JS divergence? Why can't I just use scale divergence? And one reason that we saw in the last class was that KL divergence does not take care of symmetry. And what that means is if you have two distributions, if you do the KL divergence between P and Q or Q and P, it's actually going to be different. But why does that matter to us? Why can't I just say, okay, that's fine if both of them are different. I'll just take one and use that to optimize my particular model. But there is an issue with that because both of these optimize two different things. And we'll put some math into this and bring it into perspective later in the lecture as well. But what essentially happens is when you compute the KL divergence between PX and PG, you will see that what's happening is the model says, hey, it's fine if I produce low images as long as I produce a different variety of images. So for example, if I take the MNIST data set, you will produce very bad quality images, but you will produce images from 0 to 9, which is, well, depends on what objective you want, but that's what you'll be going for. And if you look at the second term, which is PG PX, what's going to happen is you're telling I will produce extremely good quality images, but I'll produce images only for the digit 2. Both of these are not ideal because one is compromising quality and one is compromising diversity. So ideally, we want a system that's handling both of these issues, and that's technically what the JS divergence was supposed to solve. But it did not happen this way because training GANs is not really that straightforward, and we'll find out what exactly the issues were and how do we overcome them. So let's talk about the first issue with training GANs. So if you look at this, this is basically the output of a discriminator where you're going to have a, yes?
It's for a second, so. I can probably use it. Yeah, you can try that one too. You just have to stand there.
Okay. Okay. So if you look at what you have on the left, that typically looks like a sigmoidal output. You're going to have a bunch of zeros, a bunch of ones, and then you're going to have a whole lot of stuff in the middle. And when you look at the gradients of what this particular thing produces, you're going to see that at the end, it's basically going to give you very saturated outputs, right? Even if it's not a straight line, it's going to be very close to a straight line, which means at those areas, you're going to get close to zero gradient values, which means they are not going to help your generator in any way. So these are very useless gradients, so as to say. So we want most of our outputs to lie in the white region because that's where you're going to have some gradient, and that's where you're going to get some information out of the gradients that can potentially be useful to your generator. But what happens is as your discriminator gets more and more confident, your white region goes on shrinking, right? And so the amount of saturation that happens in the end, again, increases and increases. So the amount of information that you're getting continuously reduces. You're not getting a lot of information from these gradients, and so it's not going to be of much use when you're training your end-to-end system because the generator is not really receiving anything important. And as you can see, in its limit, when the discriminator gets really, really good, it's going to become a step function. And there's an issue with this because we know that the step function is not completely differentiable, right? So at the point where you wanted to give informative gradients, it's not differentiable anymore. And so your generator is not really receiving enough information for it to train. So this is an inherent problem with discriminators. It's not that easy to train because as it gets more and more confident, there is an issue of the generator not learning anything. But at the same time, you don't want your discriminator to be very bad. You want it to be optimal. And what optimal means in this case is you want it to identify the correct decision boundary. So for example, I don't know if this is going to be heard, but let's take this, right? And if you have a set of classes here, and if you have a set of classes here, um, ideally your discriminator would identify this as the decision boundary. And if it identifies this well and good, it's going to mean that your entire training process is converging and all of that. But what happens if the decision boundary it finds is orthogonal to it? Then your generator is basically going to try and generate ones here and two here or something like that. Which means even though the discriminator is getting more and more confident and is getting more and more better, it's basically modeling a wrong decision boundary, which doesn't really help. Okay, so this was the problem, and let's try to visualize it in a better way. So let's assume that we have a couple of real data points on the left and the generated data points on the right. Of course, this is exaggerated because in reality, you're going to have very small points and infinitely many points, but let's consider this for the sake of this example. So given this, the generator is going to be able to very easily identify what's real and what's fake. So it's going to have a threshold right in the middle and say everything to the right is fake data and everything to the left is real data. So your output would technically look like this. And this is very similar to what we saw before, where towards the ends, your gradients are going to be near zero, if not exactly zero. So it's going to give you gradients which are not really of any use. So when you actually put in these values of getting perfectly 1 and perfectly 0, you'll see that it all boils down to a 0, which means nothing is being propagated to your generator, so there's no learning that's going to be happening. So how can we improve on this? There are two ways that we can improve on this. The first way is if I can find a way such that the discriminator's output is not flat at the left and right, and it is in the form of the green line that you see there, then at some point you're going to ensure that at every region you're getting some information out of these gradients. Of course, as the discriminator gets better and better, this is going to get saturated and you're going to face the same problem eventually. But at the point where you need informative gradients, at the point of training, this is going to ensure that you get informative gradients. Another way that you can deal with this is by adding some noise to both of these probability distributions. And why this helps is now there is some overlap. So it's not going to be a perfectly flat curve like you see above, the red curve. So now there is a chance that you get more informed gradients using which you can potentially train your entire end-to-end system, but more importantly, train your generator. So both of these are valid ways of tackling this, but in this lecture, we are going to be focusing on the first one.
Okay, so let's take a step. Okay, am I audible? Okay, so let's take a step back and get back to where we were trying to define our goal. So what exactly are we trying to do over here? So what we are trying to do over here is try to overlap these two distributions over each other. Like that's what we ideally want, right? So in this case, let's just consider like the worst case scenario, okay? Let's consider that we have two distributions, P and Q, such that they are only one for one value of X, right? So why is this difficult? Because we want to overlap them one over the other, and if both of them are one at only one particular value, then it will overlap at only one particular value, right? So it is the worst case scenario over here. Now let theta be the distance between the peaks of these distributions. And so far, what we have talked about is KL divergence, which we use in our autoencoders, and JSD, which we sort of improved from KL divergence and started using in GANs, right? So this basically visualizes the worst case scenario I was talking about. P and Q are our distributions over here. And so if we try to calculate the KL divergence in this case, in the first case where your theta is 0, you mean that the distance between them is 0, which means that they are overlapping. So when they are overlapping, what would be the KL divergence between them? If we consider their values at x equal to 0, we would have both of their value equal to 1, and so we would have the distance to be 0, which is okay. But when both of them are apart and not overlapping, when theta is not equal to 0, and we consider the point where x is actually 0, the value of q of 0 will be what? 0. And 0 in the denominator means infinity. So here it explodes, right? Okay, so we sort of improvise that with GSD or GS diversion. And here we sort of calculated a mean of the two distributions first, and then we calculated the KL divergence with respect to this particular mean distribution. And then we have like a joint kind of expression over there for the GS diversion. So how this helps us is that earlier the value that we were getting as 0 in the denominator, it now becomes 0.5 because now we are comparing it with the mean distribution over here, right? And we now change our infinity to a constant value, which is log 2. You can obviously refer to the slides for the mathematics all there. So the point over here is that with JS divergence, you are now able to tell. So if, for example, your JS divergence is equal to 0, it means that your distributions are overlapping. And when it is log 2, it means that they are not overlapping, right? So this is what divergence helps us with. So let's see these two cases. And this visualization is already familiar to us. We just looked at it. In both of these cases, they are not overlapping, or they are like barely overlapping over here, right? But the divergence value for both of them will be constant. But is this enough? If we sort of, our goal is to make both of them overlap over each other, is just knowing that both of them are apart enough? No, right? We sort of want to know what is the distance between them. So this is our problem over here with JS divergence. So this over here, the distributions here are farther apart than they are over here. And we want to be able to quantify this, right? We want to know the distance so we know which way to go, which way to shift our distribution so that they overlap. So any ideas what we can do in this case? Any notion? No? Okay. How about we think of these two distributions and take some random points from each of these distributions and say that we have a mapping between these points. So we get some random value x and we have its generation y, and we sort of figure out what is the distance between them. Yes?
You also just use like the mean of like points of like the in yellow and the points in blue.
Right. Yeah, that could also be a way. So like where we are getting at is that we are sort of taking into account like the difference on the vertical axis, but we are sort of not, do you want to say something? Okay. So we're not sort of considering the distance on the horizontal axis, correct? So we need some kind of notion to give us information about the distance between the two distributions on the horizontal axis or somewhat like that. So this is what Earth mover's distance helps us with. So what you're ideally trying to do is you're trying to calculate how much effort does it take to move the points that you have in distribution over here to the distribution over here. That's what we're trying to do. We're trying to overlap, right? So this is how Earth mover's distance comes into picture. So this distance is also called Wasserstein distance, and it's used in WGAN, which is Wasserstein GAN. So what this basically is, it's the infimum of the joint distribution of the probability distribution of x and y with respect to the correlation of x and y, which is nothing but the mapping of which x goes to which y, which is what we were trying to do, right? And it's multiplied by the difference between, the distance between the points x and y, okay? So gamma over here basically just tells you how this x value goes to y. So the goal over here is nothing but to just find like the optimal mapping over here, the gamma, so that we get the moving, like the optimal gamma, which will help us minimize this particular distance of moving those points from one distribution to another, okay? Infimum is not exactly similar to minimum, but as a notion, we can think of it. What this is actually doing is, it is sort of returning the function that minimizes this particular expression for you, or Wasserstein distance. So there are two problems with this. One is that px is just our input images, right? We do not really know what px is, like the distribution. So how would we use that? And the other problem is that gamma itself could be very complex, right? We don't know how exactly or where exactly that particular x is going in that particular distribution. So this makes it very, very difficult problem. So this is where KR duality helps us. So what this tries to do is, KR duality, it just gives you an expression which now looks very familiar to what we are used to seeing. And this is nothing but a supremum of all the one Lipschitz functions of that particular expression. What this means is nothing, but it simply means that you are trying to bound the slopes of all the functions to a maximum value of 1 if you have a 1 Lipschitz function, and k if you have a k Lipschitz function, right? Now, why would you try to do that? Say, let's get back to the example that we took, and we have some points in one distribution, and we are trying to shift it here. So now if we could just instantaneously move, right? Let's consider our speed is like infinity, and we're just like instantaneously moving. So what information does it give us? Like one point is here, and say another point is here, and there's one that is very far apart. But if the speed is just infinity, you never know what the distance is, right? So you don't know which is far, which is near, right? So we need some finite speed limit, right? And there is wherever we have a finite speed limit, would we have a finite distance? And this is what will help us in figuring out which way do we want to go, right? So this is where Lipschitz function helps us, and which is why it is very important. Speed in our case is gradient. We want to limit the gradient. Starts making sense? Okay. So because if we did not really have this particular condition or the Lipschitz function, what would happen is we would again end up in the same situation that we were earlier. Like we know that they are far, but how far apart are they? Which direction should we move to make them overlap? We don't know that. So that is how we do that. Okay, great. We know that it is important and why we do that and everything. So how do we actually do it? Now, this is not the best way to do it, and they also mention this in the paper, but this is what they have done and left for further research at that point. So how they do this is by clipping the weights. So, for example, you have one layer over here, which is the output of your ReLU, and you pass in your function into that. So remember, the condition we were trying to follow is that we were trying to limit the slope to a maximum value of 1. And the function over here is w1x plus b1. And so if we just clip the value of w1 within some range, it would mean that we are clipping our slope, right? So if we clip the values of W1 between minus 0.1 and 0.1, it would basically mean that your slope will not be more than 0.1 times the dimensionality of the x. So now, similarly, if you have a two-layer, if you consider this for 2 layers, it would then mean a W2 and then into the output of the first layer plus B, your bias. And again, similarly, if now you clip both of them, the W1 and the W2 within some range, you are again limiting your slope. Now this will again not be bounded by 0.1 times dimensionality of x again. Why? Because we have multiple weights in picture. So again, because of the dimensionality of x or otherwise, we cannot guarantee that the function will be one Lipschitz, as the formula says. But again, it will be bounded to some finite k, and that is what we want. We want a finite speed limit, right? So this is how it's being carried out over here. So this is how we generally do this. We update our discriminator using the gradient of this expression and then clip all the weights so in theta d to some range of minus c to c. And then update our generator to minimize this negative term over here. So this is how it basically works. So now here we can see that this solves our vanishing gradient problems, which was present in the vanilla GAN version. Now if you see over here, the WGAN has linear gradients, which means it has gradient at every point in time, right? And also at any point, if you go and check, you will know which direction you want to go to. So this is the benefit of that. But one thing that is tricky over here is choosing the value of C. So if the clipping parameter is too large, then it takes too long to train the discriminator to optimality. If too small, then the gradient vanishes before reaching the generator, right? So this can be a little tricky. So this is probably not the best way to do it. So another way to do it is just like directly attempting to include this Lipschitz constraint in our equation or loss. We can easily do that by adding like a regularization parameter over here. So what this does is that it's just pushing the weight of the discriminator to be as close to 1 as possible, right? In this expression over here. It's sort of pushing it to be as close to 1 as possible. And this is what we were trying to achieve with Lipschitz also. So this will ensure that the slope will not be greater than 1. Now, the reason why this is beneficial is that if you can see over here, by changing the values of C from 0.1 to 0.001, like there's a lot of variation. But if you see the line corresponding to the gradient penalty, it is quite normal. It's still like within a range. It is, keeping it close to 1. So, which is why it's a good idea. Now, a more principled or a better way to do it is using a spectral norm. So, the slope of your Wx plus b is the spectral norm of W. And what you're trying to do over here, like the sigma of WL, is just like returning you the largest singular value of W. And when you divide the W by that largest value, what are you doing? Maximum value, again, 1, right? And everything else will follow. So again, this is a better way of doing it, a more principled way of doing it. And again, like for the notion of the composite function, so if you sort of put a bound on all the composing functions, that it means that the bound will be imposed upon the final composite function also. So this is what it uses. This is your poll. Okay. So, any ideas which ones are true? I think we just discussed this, right? So, without wasting a lot of time, B and D are true. Your Wasserstein distance basically fixes the vanishing gradient problem as we saw in the graph. And your GS divergence can avoid the exploding gradient problem, and it rather gives you like a constant value for the edge cases. So now let's come to the part where we discuss all different type of GANs. So with all its amazing applications, GAN is everywhere right now, and let me take you through some of the forms of GANs. So with the vanilla GAN version, you do not know the mapping of the latent vector space to the actual feature of the image or the actual attributes of the image. So what I mean to say is that if you have an image of a girl wearing glasses, right, you wouldn't know that what value in your latent vector space corresponds to the glasses in the image or her hair or something else, right? So we don't know this. But here, a conditional GAN can help us. So you're conditioning the GAN to use some additional information over here. Now this additional information could be in terms of labels or images or any other modality. So this is what conditional GAN basically is. So what it does is that along with the normal input, it also has some additional input, as I said, like a label. So it could be text, image, anything. So that is all that conditional GAN is. It now conditions upon this extra input also. That's all. So now if you had trained your GAN on some handwritten digits, say MNIST dataset that Harini already talked about, let's just carry that forward. So you normally cannot really control what specific images the generator will produce. So in other words, there is no way for you to request a particular digit image from that generator, right? But with conditional GAN, you can actually tell your model that I want the digit 7, and it will generate the 7 for you. So according to formula, like for formula, it's like the same formula, but instead of X, which we had earlier, now we are conditioning it with some Y for both the discriminator and the generator, right? So some interesting applications for this could be image-to-image translation. So in image over here, for example, if you give like a semantically segmented image, right, and you condition upon that image in your conditional GAN, you can actually make it to generate some realistic output. Similarly, over here, if you just give like a edge image over here, it can generate like a nice bag for you here. So this is something that is interesting that conditional GAN can do. And something that is very common nowadays is text-to-image synthesis. So in this, we just condition our GAN on some text prompt, and then our model is able to generate some image based on that. So as we can see, like stack GAN, which is a version of conditional GAN, is able to produce much more better results than a vanilla GAN because it conditions upon the text given to it explicitly. So now, next let's discuss cycle GAN. This is interesting because it was the first, I think it got popular because it was able to do image translation, which was not possible before that. And what image translation basically means that if you have two objects that look similar in size and structure, you can like generate images taking their similarities. So for example, over here, if you have like an image of a zebra like that and an image of a horse, you could create a horse that looks like a zebra and a zebra that looks like a horse, right? So that's what it can do. But why cycle GANs? Like, why can't we use any of the other methods that we have used so far? Sure. Could we use like our autoencoder that we have learned about? Anyone, any ideas why this would work or not work? Okay. So for this, for autoencoders, we would generally require like image pairs. So autoencoders would require you to measure the reconstruction error between the input and the output, right? And it will not be possible for us to get images of zebra and horse that have the same pose or the same background. So how would you assess that? So this cannot be done. But how about a better version of that? Say we put it into our vanilla GAN. You have the input image of a zebra, you put it through a generator and generate a horse. And this now goes into your discriminator to decide whether it is real or fake. So the problem with this would be that once this particular image is generated and it sees a horse, the discriminator would keep on learning to like see whether this particular image is a real horse or not. And though the generator will try to fool the discriminator, it'll still try to just generate these images of the horse without actually correlating to the input. So what we also need is, we also need a way to make sure that the produced image is closely related to the input image for the generator. So which is why a normal GAN would not work. Now, as opposed to this, what a cycle GAN does is, it takes the input, it passes through one generator to produce this particular output over here. So it generates the horse image. Now it passes this generated image again into another generator, and this particular image that it generates is ideally supposed to be the same as the one it was given in the first goal, like the same as the input. So now we can calculate the reconstruction loss for this, right? So this is how your cycle GAN works. It's called cycle because it goes in a row and it sort of wants to come to where it started from. And so on top of regular GAN, like training to ensure the generated image looks like a zebra. So we are trying to, with this cycle consistency loss, we are trying to ensure that it is similar to what it was given, basically, right? So what do we learn from cycle GAN? So we do not have any paired data set of zebras and horses, right? Or converted images, like zebra converted to horse, the horse is converted to zebra. We do not have these paired images or data set. So there is no easy discriminative method to train zebras from horses, but we are still able to do this via GANs. So we can train distributions to match, and this is done only via cycle GAN. Now, other similar procedures that are present today, one of them is neural style transfer, because cycle GAN is also used for style transfers. So this is another way, another method to do it. So what a neural style transfer does is it takes one content image and one style image. So now it uses CNNs to sort of come up with content statistics from content image and style statistics from style image, and it sort of merges both of them to come up with an output like this. So one thing is that it's different from, we'll obviously come to that why it's different, but just to give a crux, it's different from CycleGAN because it needs these specific images, a content image and a style image. As opposed to that, if you have a style transfer with CycleGAN, if you give it just an input image and say that you want a Monet style or a Van Gogh style or a Cézanne style, sorry, then it'll directly be able to do it given that all these are domains for it, right? So once you give an input image, it'll just be able to convert it for you. So when we try to compare it, these are the differences. And just coming to a point where you would want to choose either of them. So when would you use a neural style transfer is when you have like specific images and you want more control over the image that is generated and you have small number of images in general. As opposed to that, you would be using a CycleGAN when the specificity of the image does not really matter as much. Now, from CycleGAN, we see that we were using two generators and a discriminator, right? Now, say I have three animals. I have a dog, a lion, and a giraffe. And now I want to train my model so that if I want to generate an image of a dog looking like a giraffe, I would be able to do it. If I want a giraffe looking like I think I forgot, but if it was lion, so lion, then it would be possible. What I'm getting at is that if you want all these kind of combinations in there, we would need multiple models if we were just using a CycleGAN. So we would need like a set of two generators and one discriminator for each pair, right? And that's a lot of models, right? We do not want to do that. So StarGAN is like a generalization of CycleGAN, which lets you deal with more domains at once. So this is not very complex. I think looking at it, it looks like, okay, it's like a different, completely different method. But what it actually does is it just adds one more dimension and takes out like a one hot encoding for the domain and just adds it to the dimension and trains it. So if you have like 3 channels RGB, you'll also take the target domain along with it while training and then continue it. So what it tries to do is it has the input image and the target domain, which will be one hot encoding of that how many ever domains you have. And then you pass it to the generator, which will then produce a fake image. Now this will again go with the original domain. So again, it is training with the original domain that you had fed it in, like the fake image, goes into a second generator, and then the reconstructed image is generated, and then similarly the loss, whatever was happening in CycleGAN, similar stuff, and then the discriminator and everything. So the difference here is what? Even CycleGAN was able to tell you whether it is real or fake, but here you are also able to figure out what domain does it lie in after the image comes out, after it's generated. So an example would be like this. So your input image could be like just an image with some sort of extra label, say RAFD label, which sort of tells you what is the mood of that particular person at that time. You pass it to the generator, and then once that image is generated, you again use that along with the original domain label into the next generator and get the image. Now in the end, along with the generated image, and whether it's real or fake with the discriminator, it will also tell you this RAFD label. RAFD label, again, it's nothing but that extra particular domain label that you wanted to give it. So if in our case it was like giraffe and dog and lion, it would just give us which of them, yeah.
I guess like with that, how do you know how many domains to have initially? Like for example, like you just pick a giraffe, lion, and more, but and this example is like angry, fearful, happy. Like if you wanted, is there a point where if you put too much, you'll just get like bad results? So
I don't think so. It's just like you're adding more classes, right, to your model. So what are your objectives of the star GAN? So again, as we discussed, the discriminator will tell you whether it is fake or not, and also predict the target domain of the input image. And this uses the auxiliary classifier to learn the mapping of the original image and its corresponding domain label from the dataset. And as for the generator, it is able to generate a realistic image, and the images, it has to ensure that the images that are generated are classifiable as target domain by D. And this, again, like we are still like, this is a generalization of the cycle GAN. So we are still using the cycle consistency laws. So we should ensure that it is similar to the original input that we gave. So how much time do we have? Oh, okay, cool. So another interesting type of GAN is bidirectional GAN. So as we have bidirectional everything now, like over here also we are trying to train the encoder-decoder pair in a elegant fashion. So here the main point is that BiGAN tries to learn the inverse mapping. So we generally get the data from the latent space, but now we are trying to put the data back into the latent space. So we are trying to learn the feature representation of the images, which is called feature learning. So we are actually trying to get rich features from our model. So here again, like there is no right or wrong answer of whether that feature is right or wrong. Like for example, if I have to describe a dog, I would say something else, and maybe Harini wants to have like different set of descriptors for differentiating it from a cat. But again, like the bidirectional GAN helps you in cases like this. It helps you get good feature representations. So this is what the architecture looks like. It basically takes the latent codes, passes it into a generator, and generates an image. And then another module we also have is the encoder, which takes the image and generates the latent codes. Now the discriminator here does not only take the image, but also the latent codes that were learned, that were encoded in the encoder. So both of these together are taken by the decoder, and then we get to a conclusion whether it is a real image or not, or a fake code or not. So it is sort of a case where you are more concerned with getting more rich features in general than wanting to classify whether it is this or that. Any doubts so far? Yeah.
Why are we learning the latent codes before?
Here? So again, so in your homework 2P2, while you were doing verification, why were we trying to get more rich features? Why were we trying to get a better feature representation? So similarly, so if you have a good feature representation, you will be able to use it for multiple tasks, right? So yeah, I mean, that would be the answer. Have anything to add? Okay. So another type of GAN is a Laplacian GAN, which is sort of constructed as a chain of conditional GANs. So it is basically just like one conditional GAN after the other with some added noise. So how it looks like is this. You have an image, you have some noise, you get some output from your conditional GAN. Here again, like in a conditional GAN, you're supposed to provide a condition. So you're conditioning it on the image. And then the output that you get, you again pass it to another conditional GAN with some added noise, and you keep on doing it until you get your desired result. So how it helps is that generally when you're working with a smaller area, you get better results. So when you like keep on repeating the process, it can help you like get a better quality of the image and so on. So this is what Laplacian GAN does. And we have many other GANs. We also have for all of these different type of GANs that we discussed, we have like a link for each of these papers if you would want to go through it in more detail. So a summary for everything we've learned so far. So training GANs is difficult for a lot of reasons. Primarily, the issue of the discriminator capturing the wrong boundary, being too confident or not differentiable and getting saturated due to the formulation of the objective. We can remedy this by using the earth movers metric or the Weissenstein distance. The Lipschitz constant of WGANs can be imposed in several ways, including weight clipping, gradient penalties, and spectral norm. There are so many variants of GANs which do more than just image generation and are able to do image translation or style transfer. These are references. Any doubts? Okay. Yeah, then we are done for the lecture today. Thank you, everyone.